Welcome, dear students, to this class of name reaction where we'll be dealing with Sharpless asymmetric epoxidation, a very, very important reaction for which Sharpless was given the Nobel Prize in the year 2001. His work is published in the Journal of American Chemical Society in the year 1980. Through this reaction, allylic alcohols, they are converted into epoxy alcohols. And this reaction is very chemoselective. Chemoselective implying that only allylic alcohols can react, no other substrates. So only the double bond which is present on the allylic alcohol, that double bond is the one which forms an epoxide, irrespective of how many double bonds may be present or how much unsaturation there is in the entire molecule. The most important part is that this is giving us an enantiomeric excess that above 90%. So we are getting a highly pure product. Moreover, the chemoselectivity is there, as I discussed, that only allylic alcoholic groups are the ones which are present, those double bonds at the allylic alcohol attached to the alcohol, they are the ones which are forming the epoxides and no other double bonds or no other unsaturation in the molecule. And the most important part, another about it, is that the epoxides which are formed, they can be easily converted into other very important compounds like amino alcohols, diols, ethers, and these are important functional groups in many bioactive compounds as well as natural products, which form as the lead or the basis for preparation of various types of active molecules. The substrate scope is that it includes many primary alcohols and secondary alcohols. All should be allyl. And the products are predictable, as I've been saying, that is stereospecific. We can predict as to which type of product will be formed depending upon what reactant we have selected. So now moving on to an overview of this reaction, where an allyl alcohol is converted by using diethyl tartarate, TBHP, and the catalyst titanium tetraisopropoxide to convert it into the epoxide. Now what is happening is, because this double bond, as we can see, is a prochiral center, and when this epoxide is formed, we get a chiral product which is enantiomeric and can be diastereomeric if any other chiral center is also present in the entire molecule. Then we get a pair of diastereomers. But the chemistry at the epoxide formation is the one which which is undergoing the change, because it is prochiral, not chiral so far. It becomes chiral by the action of these reagents. So what is most important is that we are getting these. Why? Because we are using these reagents that are used here in the Sharpless epoxidation is diethyl tartrate. Now diethyl tartrate, the ester of tartaric acid, is chiral, and it can be minus or it can be plus. That is, it can be RR or it can be SS. RR is the one which is plus, and the one which is minus is SS. And the one which is SS can also be written as D. The one which is RR can also be written as L. And as a result of this, because we are using tertiary butyl hydroperoxide, that is TBHP, tertiary butyl hydroperoxide, and at the same time this catalyst, this peroxide is the one which will introduce the oxygen for epoxidation, and the catalyst uses titanium tetraisopropoxide. So we are getting an enantiomeric excess of over 90% by formation of these epoxide alcohols. Now, as to how the mechanism proceeds, it's very interesting because the mechanism, the displacement of the isopropoxide ligand takes place on titanium by DET. So, how this is proceeding, so that the chiral DET is acting as the chiral auxiliary, means it is just guiding the reaction, guiding in the sense as to where the epoxide oxygen has to be delivered, on which side. That is, it can be delivered from above because there are two faces to the double bond, from above or below. That is the guidance. That is why it's called a chiral auxiliary, because it itself is removed at the end of the reaction. It just guides it to that certain location. And hence we can predict what type of product depending upon this chiral auxiliary, whether we are using a plus or a minus, as to which product will be formed by this allyl alcohol or the allyl substrate, which can be primary or which can be also secondary. Now, for simplicity, I've shown this cycle here, and rather than titanium, because it acts as a dimer, but is here we've depicted it as a monomer so that things don't become too complicated as long as we understand the process. So, here is our titanium tetra isopropoxide, and what is happening when it is reacting with this diethyl tartrate? This is diethyl tartrate, which is shown here, the -1 minus diethyl tartrate, which can also be called as D or which can also be called as SS. So this is diethyl tartrate, CHOHCOO, ethyl CH2 CH3. Similarly, CH2 CH3 is this end. So the ester of tartric acid, chiral. Now, what will this do? This will change this. Why? Because H's from here, the from these two hydroxy group will change it into isopropyl alcohol. Now we are preparing this, the diethyl tartrate, for attachment towards this titanium, the catalyst. This is the chiral auxiliary which will guide. So now when two of them are removed, these two removed at those position, see what has been attached. This is one oxygen of OH. This is the other oxygen of diethyl tartrate. This is the rest of the molecule. It was OH here. The H was from here. Reduce this into alcohol. It itself getting oxidized and attached here by these ligands. Oxygen. The two oxygen belonging to diethyl tartrate. Then in the next, because this is the catalytic cycle, in the next, see, this is the tertiary butyl hydroxy peroxide. Now we'll begin the delivery of this oxygen guided by this diethyl tartrate, which is attached to titanium because the H and the H from here have been used up because two such entities have been removed in the form of alcohol. So this has taken the place. Now what will happen in the next step, as this will react, then another of this OIPR from titanium, this propoxide, it is reduced to the alcohol. Okay, why has this been done? This is reduced to the alcohol, taking this H from here, from the hydroperoxide. Why? Because this oxygen can now be attached in place of this. So gradually, one this entire diethyl tartrate, then the another molecule of this R peroxide forming reagent, TBHP. This was attached because H was removed. So by virtue of O. So you can see O, this is of this, and tertiary butyl group attached to titanium. So this has also been inserted. Now we are ready for the formation of peroxide. So here comes the next, that is our substrate. The substrate, that is our allyl alcohol. So the allyl alcohol, how will this then be inserted? Because see, through these pi bonds. These pi bonds are now exchanging. See, pi bond here on this titanium, and titanium already, which is attached to these oxygens of the diethyl tartrate, and this other oxygen of the TBHP. So this is attached here, and at the same time now this is the other, that is the allyl alcohol oxygen. So you can see this is the allyl alcohol oxygen. This is how it's aligned itself. So how this is guiding, because from one side this is covering the molecule, so hence this is guiding it to the other side. Guiding what? Guiding our substrate to another side. So what will happen on this substrate, because this already is linked here, this TBHP, the delivering agent, what will this do? This will therefore tend to form, this double bond will open up, and what will be formed? An epoxide. The epoxide has been, this is now delivering. The epoxide has been formed because this has got two oxygens. So this has been delivered, this oxygen from the TBHP. Where? To the double bond. And which is the factor guiding it? It is this diethyl tartrate. Now, depending upon plus and minus, we'll take up the stereochemistry later on. This is just to understand the mechanism. So, this peroxide has delivered the oxygen onto this double bond. This oxygen has been delivered here, forming an epoxide ring. And as you can see, this alcohol is attached, this allyl alcohol, by means of this oxygen here to the titanium. Now, in the next step, as we can see, what will happen? That once this has been formed, now this is tertiary butyl. This hydroperoxide is no longer there. Only one oxygen is left because this other oxygen is being delivered here. H was removed even earlier. Now, once this has been formed on this catalyst surface, now what will happen in the next step? That this will tend to leave with an isopropyl, because we've got isopropyl alcohol. As you know, it was formed earlier in the cycle. So with this isopropyl alcohol, what will happen? That this will be reduced and this will be oxidized. So this will be reduced and removed from here. In other words, we have got our product, that is the epoxide has been formed. O and an H from where? H from here. The OH, H from isopropyl alcohol. And this O, then therefore, which is removed, will be again attached to this position from where what has left? This allyl alcohol portion attached by O. H was removed earlier, as you saw in the cycle. So now we have got this and we have got our product. The product has been formed. Now, simple, another uh, uh, repetition of such an act, another molecule of isopropyl alcohol, what will it do? That it will reduce this to tertiary butyl alcohol and itself be oxidized and attached to our titanium. So here our catalyst is recovered. The catalyst along with this DET has been recovered or regenerated, as we can say. So this was the entire cycle whereby we got our epoxide was formed. How? By means of this cycle where gradually, this DET, diethyl tartrate, is being inserted onto this titanium. How? From two position, this O and this O, the H being removed as it reduces these two to isopropyl alcohol. Once this has been introduced, then the next step is the introduction of this peroxide, TBPH. This too is introduced by virtue of this oxygen because H is removed again in the form of isopropyl alcohol. So another position is free on titanium. Earlier there were four such. Now these are gradually being removed one by one. You can see. So this is now attached here. So what will happen to the titanium? See, titanium, now tertiary butoxide, this has been attached here by means of these. It has got two oxygens because. So these two now. Earlier there were four isopropoxide tetra. Now in place of that, now there's diethyl titrate, which is guiding the entire reaction, or the attack of the what? The attack of the peroxide oxygen as to from where it should attack. This is the one which is guiding or controlling chiral auxiliary. So once this has been attached to titanium, now will become the delivery on the our allyl alcohol. Our allyl alcohol is again on the, because see there are these two oxygens, so one of the oxygens will be attached in the form of the epoxide to this, and the other oxygen of the our allyl alcohol will attach here. So what will happen as a consequence? An epoxide formation will take place. This epoxide is formed, it's still attached by means of the other alcoholic end where H is being removed. Now this is then reduced by isopropyl alcohol. So this is regenerated, our product is regenerated, and at the same time we get this OIPR, that is isopropyl alcohol, which was oxidized, is attached to this in place of this epoxide which has been eliminated in the form of the alcohol. And this again by means of isopropyl alcohol, this is converted into the tertiary butyl alcohol, and while this is this one is oxidized, this is reduced, this is oxidized, so this gets attached and we get our catalyst. This is catalyst with which we started after the attachment of this diethyl tartrate. So this in brief was the mechanism, and now we will come to the important aspect, that is its stereochemistry. Now the stereochemistry is, I've simplified it to the best of my knowledge as far as I could because there are various methods of determining it. So let's see. I hope you will find this simple and easy to comprehend. See, there is diethyl tartrate, which I have written as here, diethyl tartrate, the plus, which can also be written as RR, okay, in the question paper, it's the same. Or it can be also written as L, plus DET is the L1. And the delivery of oxygen is re. Now, because see, it's a double bond, so we have to remember our re sign nomenclature from the re end. You'll soon see as to how. And if it is a minus diethyl tartrate, which can also be written as SS, it implies the same thing, or it can be written as DET, diethyl tartrate. The delivery in this case of the oxygen or the epoxide formation is on the psi phase. Now, in place of this, we can also use other esters are also can also be used like DMT at times. It's, you can see depending on the convenience and the situation in the reaction. DMT is nothing but dimethyl tartrate, or DIPT, which is again the other ester, diisopropyl tartrate. These can also be used for this reaction. Now in each and every reaction I've just written it as Sharpless because you know now all the reagents which are used. So Sharpless I've written because the catalyst titanium catalyst, and the peroxide, that is TBPH. So now TBHP, sorry. Now see here, this is the one which is important, plus DMT. So how do we know when it is plus DMT, dimethyl tartrate? In that case, what type of epoxidation, whether it will be psi or Re. And as we know that plus is always aligned with the catalyst in such a way, because plus implies RR. So it is attached, plus dimethyl tartrate means implies the RR stereochemistry at the two chiral centers. So it is attached on the catalyst in such a way so that the delivery of the oxygen takes place from the Re side. That is all we have to remember, Re. So now let's see, if we take, this is the double bond, and we take out as to what side this is on the plane of the paper, whether it is Re or whether it is psi. So this we can select it at that center. This we will select for calculation because this is the one which is attached to this allylic OH. So remembering our CIP nomenclature, Kahn and Gold prologue. So this will be carbon number 1 because this C and this is O. So first priority. Then here this is C and another C. So second priority. And this here is H. So third priority. Because this is phase, so there's no fall because there are no falling. This is a double bond. So this is a chiral phase, prochiral phase. So now let's see what is the direction going from 1 to 2 to 3. The direction is what? Anti-clockwise. In other words, this phase on the plane of the paper is depicting what? Our psi phase. But we have chosen this as our chiral auxiliary. So this we know guides the oxygen towards the Re. So if this thing in the plane of the paper, this surface, is the psi, that means it will be delivered below this surface because that will be the Re phase. So in other words, we will get this as the product. I hope you followed it. This will be the product because we are taking this out on the plane of the paper. So plane of the paper, when we fix these priorities, we are getting what? We are getting this as the psi, anti-clockwise. So that means below this plane of paper must be the Re because plus DET delivers it oxygen on the Re. So oxygen, this will be the product form. The epoxide formed will be on this side, below the plane of the paper. Now coming to the next example. In the next example, here we can see, again I've written just Sharpless because we know what is being used. The reagents, titanium and this hydroperoxide, tetrabutyl hydroperoxide, TBHP. So now this time we have used DMT. DMT is what? This ester. Plus means RR. At the two centers, the chirality is RR. Dimethyl tartrate. Not ethyl this time, it's dimethyl tartrate. So let's see, depending upon what surface this is on the plane of the paper. This is number 1. This is the chiral phase. So this is number 1 because carbon, here too there is carbon, but here carbon is attached to oxygen. Here is carbon is attached to another carbon. So this will be the first priority. This will be the second. And here, this will be the third. So what are we getting this time? This time again, this is anti-clockwise or psi on the plane of the paper. So in other words, the epoxide oxygen will be delivered by the DMT on the lower phase, that is below the plane of the paper. So this will be the product that is formed, and you will be surprised to know that when work, these are reported papers, not my own work or something. And just so see, this will be 95% purity. Can you imagine enantiomeric excess of this epoxide? Such a high stereo selectivity or enantio selectivity, and the yield is also 45% yield. And this is an important intermediate in this production of this antibiotic methicene. So this is used there, methymycine. Now let's see the next example. The next example is of this type. Here, as we can see, again we have this allyl alcohol, carbon-carbon double bond. Then this double bond vinyl and the third one attached. Then this is allyl. So this is allyl alcohol. Now allyl alcohol. Now again Sharpless, the same reagents. By now you must be well versed with the reagents. Titanium tetraisopropoxide and the other one tetra butyl, the hydroperoxide, TBHP. Now this time one has selected the chiral auxiliary as DIPT because we know what type of a product we want. See, it is specified. That is why this reaction is specific. We can predict what type of product will be formed if we are using this. How can we predict? Again, see, 1, 2, 3. We have calculated on this chiral phase. This comes to what? 1, 2, 3 anti-clockwise. That is, now the plane of the paper itself is what? Which phase? It is anti-clockwise. In other words, it's the psi phase. So the oxygen will be delivered here. That is above this plane of paper. So this will be the product that is formed. And as shown here, again, this is 58% yield, 95% enantiomeric excess. And this is an intermediate for this antibiotic like the earlier one. This is for erythromycin intermediate, this product that has been formed. So now you can realize the importance of this reaction as to how important they are. Now let's see another example. In this is the molecule. And here this time what has been taken? Plus DIPT. That is, this one now is diisopropyl tartrate, the ester, DIPT. Now, once again, we start our numbering taking this chiral phase. Chiral phase is the one which is attached to the alcohol function, CH2OH. From there, we start our numbering. So this will be 1 because CO. This is again, this is attached to CC. So this is 2. And this here, there's nothing. That means over here naturally a hydrogen, the fourth valency hydrogen. So this is third priority. Going in this direction again on the plane of the paper, this is which surface? This is psi. So oxygen won't be delivered here. It will be delivered below the plane because we are using plus, and we know plus DIPT or plus DEPT if had been taken. These plus chiral auxiliaries, that is the RR ones, they deliver it from which end? From the re. And this surface is what? On the plane of the paper, it is psi. So it will be below the plane of the paper. So this is the product which is formed. And this is 80% yield, very good yield. And 95% enantiomeric excess. And this is a leukotriene intermediate. Intermediate for preparation of leukotriene. Now let's see a very interesting problem based on all these. I basically tried to deal with as much as I could in this short span of time. Provided you understand the steps, you will see that it's not difficult at all. So here, see now, this is our reacting molecule, the substrate, and a number of such reagents are given. As you can see from this, you can make out like triphenyl phosphine, this phosphorus triphenyl attached to, now this is, we can. So now let's try to solve this problem, a very interesting problem as I was saying, because see here a number of reagents are given. So one will be wondering as to what is going to take place. Nothing like Sharpless seems possible over here, but let's see the reagents one by one and organize our work. So the first thing comes to our notice is the Wittig reagent. With phosphorus, a Wittig reagent. So sodium hydride Naturally, we are all very familiar, so I'm not going to discuss the reaction. I've discussed this reaction earlier on in detail, dealing with the stereochemistry and also with the E and Z forms as to which halide will form, which type of a compound will be formed, alkene will be formed. So let's see with this when NaH, now NaH base, so CH2, when H positive is eliminated, we get a carbonyl. And what sort of a halide is formed now? The halide which is formed is a stable halide because it's got an electron pulling group. Unstable means the negative charge is increased even more had it been R over here, unstable, but this is stable, huh? So now because of the stable halide, we'll get this alkene, and the alkene which will be formed will be what? It will be trans because this is stable. The halide is stable. Carbon negative has been stabilized by this group, so this is a stable halide which is formed. So we will get due to our Wittig reaction. So these two are indicating the Wittig or alkene, trans you know very well because carbon number 1 over here, priority number 1, number 2, this double bond and 1 because this got CC and 2. So trans is formed, E rather, we'll call it E. So, and this indicates reduction specific. This is specific for carbonyl. So this, this will reduce only the carbonyl. This one. So what will happen? Carbonyl reduced. Not this double bond is not affected. So as a result of that, we will get CH2OH, and now we can see our next reaction. Why? Because all these reagents propose a Sharpless epoxidation. Okay, so Sharpless epoxidation, and this is an allyl alcohol, and these are the reagents. Of course, minus DT is here. So we have to take into consideration what type of an isomer will be formed. Find the product. Let's see whether the surface of this Re or Psi. So this is the center chiral face. From this face, we'll see the Re and the Psi aspects. So this is now C with an O first priority. Then this is C3. This is second priority here. This is third. Moving along this, we get what? An anticlockwise, that is psi phase. So above the paper is the psi phase. Hence, this type of an epoxide will be formed. So I hope you understand this interesting problem which was given in one of the competitive exams, whereby uh, we are associating both our Wittig as well as our Sharpless epoxidation. The Wittig gives this trans stabilized halide, gives this E alkene. The E alkene reduced by the specific lithium aluminum hydride, which is specific for the carbonyl. So this remains unaffected. So this is reduced to alcohol. And now this is the allyl alcohol. Allyl alcohol with Wittig will be reduced, will be forming the epoxide. And which type of an epoxide, above the plane or below the plane, we'll see by the Re and Psi. And so assigning that this is first priority CO, C within, and this is second priority, this is third. This is what direction? Anticlockwise, so psi, and since we have taken minus, so we know above the plane here on the plane of the paper it will be psi, so this type of an epoxide will be formed. So that is all for today. I hope you were able to understand the basics, the simple type of product formation by using the Re-Psi method, though there are various other methods also available, including the mnemonic method, but somehow I felt this was far way simpler to understand also, and at the same time gave us the right type of the product without any confusion. So whichever you can opt for whatever method you want to, and hope you understood the class properly, were able to follow all the steps, and as to the uses of this very important reaction that we just studied, the interesting aspects as to why he was awarded the Nobel Prize, because as you can see, this epoxidation is leading to so much of enantiomeric excess, a high purity compound, and these compounds are very much used for the preparation of different types of bioactive molecules and natural products. Why? Because the epoxides can be easily converted into diols, amino alcohols, and ethers, which are all important functional groups in these bioactive molecules. And the substrate scope in itself is inclusive of primary and secondary allylic alcohols. And there is product predictability. That means we are the ones we can design our synthesis depending upon the type of product we want to have, which type of selectivity, which type of product we want to have. Accordingly, we can design our synthesis and get a good purity compound. And moreover, the reactants are also very cheap and easily available. So that was all for today. Thank you.